All right, we are getting to the end of our study of exponential functions. We're in 5.11. The start thinking part says a bank pays out 4% per year on the money deposited into a savings account. Explain why interest paid on the account in 10 years does not simply add up to the same as if you did 40% payment, even though 4% for 10 years equals 40%. So the reason why this grows faster than that is because how a bank works is you are going over, usually you are getting paid on whatever the balance is in the account. So after the first year, you have your original money, then you also got interest, and now that is added in there. So there's actually more money in your account, and you are going to be not only getting interest on the original amount, which is called your principal, but you're going to get interest on the interest. And then the next year, you're going to get the interest on the interest and the interest on the interest of the interest. And that makes it so that it grows a bit quicker. If Kendrick invests $100 into the account, how much will it be after 10 years? So we know how to write this equation. It's 100 times 1 plus 0.04, 4%, to the 10th, and you end up getting 148.04. Sorry, 148.02. Now, if you just do 40%, if you said 4% for 10 years is 40%, 40% of 100 is $40. So you would only have gotten, if you only were getting interest off of the original, you would get $140, where since you're going to keep getting interest off the interest off the interest, and it keeps going, you end up with $148. It's not that much of a difference, but over time, it actually adds up quite a bit. In this case, you end up with $8 extra. If you're paid interest on the money that is currently in the account at any time, they look at that amount and they take a certain percent of it. Would you rather be paid more frequently or less frequently? The answer is you'd always be wanting to be paid more frequently. The reason why is if you're paid more frequently, then the balance is going to increase more often, and you are going to be paid interest off of interest off of interest more frequently. So this concept here is called compound interest. Compound interest is basically saying that you are getting paid interest not only on the principal, which is the original amount you put in, but you're going to get interest off of interest. So by default, the equations that we've been making, the exponential equations, are accounting for that. They're going over and getting the new amount and then taking a certain percent of that. And then you have a new amount and you take a certain percent off that. So we've already been doing kind of a compound interest. I'm going to show you how it's a little different in today's lesson. So in this application, it says the equation that represents the amount of money in an account that pays 12% interest per year with an original balance of $5,000 is y equals 5,000 times 1 plus 0.12 all to the first, and that'd be if it was going for 1 year. Now, let's say you said, I don't want you to pay me the full 12% at the end of the year. I'd rather you just give me a little bit each month. So if they don't want to pay you more than the 12%, but they're going to pay you each month, how much would they pay you per month? Well, this should make sense that if they give you 1% per month, then after 12 months, it's going to add up to be 12%. So that would be the case. So you'd want to be paid 1% per month rather than just the lump sum at the end. What part of the equation would need to be altered to represent that you're not being paid the full 12%, but that you're being paid 1% each month? And it is going to be the 0.12 needs to be changed to 0.01 so that it's 1% and not 12%. And the way you could think of this is take your original, which is 0.12, 12%, and divide by the number of times they're going to pay you. So the number of times they pay you, if they're paying you monthly, is 12 times. That tells you you're getting paid 1%. Now we have to alter another part of your equation here. So the other part is, it says, now you're not just getting paid once at the end of the year, you're getting paid a less percentage, but way more times. Now, instead of going over and being paid once at the end of the year and getting 12%, if you get paid 1%, how many times do you get paid over the year? And that makes sense that you're going to alter the exponent part. Instead of it being a 1, meaning you're paid once, you're getting paid 12 times. So you need to make that a 12. Okay? So think about this, what they're saying. They're saying instead of paying you 12% one time, they're going to pay you 1% 12 times each year. Now, while that seems like, why would you do that? it actually works out in your favor, because after the first month, you go over and you get paid your 1%, and now the second month, you're going to be paid on your principal and that 1%. And then the next month you get paid and your account balance goes up a little bit, and they take a percentage of that. And then your account balance goes up a little bit more the next month. So you're going to find that this type of compounding actually helps out, not by a lot, but it's better to get the dollars in your pocket than theirs. Now, the last part here is, let's try to figure out how we can make an equation that is general for compound interest, not just compounding once a year like what we've been doing, but in general, compounding every month, every day, every week, something like that. So the equation is A equals P. That is your principal. That's just your original amount. Our equation usually has looked like that. You still have the 1 like normal. But the next part is, rather than being paid the full rate, you're going to divide by the number of times they are going to pay you. So if they pay you once a year, then you're going to divide by 1, and it's just the normal rate, the way we've been doing things. If they pay you twice a year, you're going to divide by 2. So you're going to get half of the rate twice a year. If they pay you every month, you're going to divide by 12. So you're going to be getting a 1/12 of what you normally would get. Now, you have to change the exponent on the outside, because you're not just getting paid the same number of times, which was once a year. Now you're getting paid many times a year. So if you are doing it monthly, for every time you normally would get paid once a year, you're going to get 12 of those. If you get paid twice a year, then it's going to be 2 times whatever you would have been paid by. So that is the N times T. So there is the general equation. It's pretty much the same as what we've been doing, except for the rate is being divided so that you're getting paid a portion of that percent more times. So rather than getting 12% once a year, you get 1% 12 times a year. And it actually works out in your favor. Let's go ahead and take a look at this application here. It says Tyreek inherits $100,000 from her grandma. She's deciding which bank to put her money in. Bank of America pays 3.8%, but they only pay it once a year, and that's at the end of the year. Ally pays 3.8%, but they're going to compound it monthly. They're going to break that 3.8% up into smaller amounts, but they're going to pay it to you 12 times a year. And then Chase Bank is going to break it up into very small marks of that percent, but they're going to pay you daily. So it is going to be a very small amount, but they pay you each day, which is kind of cool. It says, how much more will you make with Ally and Chase since they are compounding throughout the year? So what I did was I generated all of my equations here. You could see the first one. Technically, when you simplify that, it just comes out to be the equation we normally use. The next one, you're taking your percent and you're dividing by 12 to find out how much they need to pay you each month. And then rather than paying you just 10 times over 10 years, since it's 12 times per year for 10 years, they actually pay you this tiny amount 120 times. And then the last one, you take the percent, you divide by 365. It's a tiny percent, but rather than paying you that amount 10 times over 10 years, they're going to pay you 3,650 times, because it's once a day for 10 years. When you go over, you can see how I use parentheses when I'm putting it into my calculator. You end up getting $938 more just by compounding and be paid a little bit more, or sorry, a portion of it each month. And then you make $1,023 more if they go over and pay you each day. And once again, the reason why this works is if they pay you a portion of it after 1 month, then not only are you getting paid on your principal, you're getting paid interest on that interest already. So that's why compound interest is great. If you're making money, you're going to see that it's not great if you're losing money. So in this one, it says Yanni goes over and starts the first year of college, gets a $10,000 credit card, maxes it out, doesn't like college, drops out, decides I'm not doing anything with college. I'm forgetting about it all, just sets the credit card bill aside, ignores the letters that come in. How much does she have to, or how much does she owe after, it says 14 years? It's going to be at 21%. Every month that you don't pay, they are going to compound it at that. So this is basically saying $10,000 at 21% compounded monthly for 14 years. When you put all that into our equation, it comes out to be $184,000, which is insane. Now, if they only charged you interest on the original amount you borrowed, 14 years, 21% per year comes out to 294%, which means that you would have to pay $29,000 on top of the $10,000 you borrowed. So really, if they only charged you the percent on the amount you borrowed, you'd owe $39,000. Since they keep charging you interest on the interest of the interest of the interest of the interest over and over and over many, many times, you end up owing $184,000, which is bonkers. Obviously, I rounded that down. It's $184,409.04. The last one says, Ken borrows money from his parents. The equation that represents the amount of money he owes after a certain amount of time can be modeled by the following. Use the equation to answer the following questions. What does the 4,000 mean? That's called your principal. It's the original amount he borrowed. What is the 0.06? They're charging him 6% per year. What does the 2 mean? They're asking for money twice a year. Every 6 months, they go over and charge him a portion. So they would charge him 3% after the first 6 months and another 3% after the next 6 months, which comes out to be that 6%. What does the 7 mean? He's going to have that loan out for 7 years, okay, before he starts paying it back. Let's go ahead and take a look at the homework. It says Meredith deposits $8,000 into an account paying 6%, which is compounded monthly. The simplified equation that represents the amount of money she has after 5 years is 8,000 times 1 plus 0.005 to the 60th. And the question is, what are these numbers? This is the equation after it's been simplified. It says, why does it say 0.005, so 0.5%, even though she's supposed to be paying 6%? And the reason why is that if she's paying 6% a year, if they charge it to her monthly, when you divide the 6% by 12, you end up saying, you owe me 0.5% each month. So that is what the 0.005 means, 0.5% per month. Why does it say 60? Well, over 5 years, normally you'd pay 5 times, but this is saying you're paying a smaller percent, 0.5% instead of 6%, but we're going to charge you monthly over 5 years. So that comes out to you pay 60 times over that 5 years. That's why it's a 60. Why do you end up with more money in the account that pays interest compounded daily rather than once a year? This one's not compounding daily, but it's just asking the question, and it's because you are able to be paid interest on the interest more often, and your balance is going to increase more frequently. Number 3 says Marco owes $12,000 a credit card. The credit card company charges 21%, compounded monthly. How much will he owe in 6 years? You could see how he put that in. The 0.21 divided by 12 tells you what percent you are paying each month. It's going to be less than 20%. It's going to be a 1/12 of that. And then you are going to pay that amount many more times than you normally would. Rather than paying 6 times at the end of the year, you're going to pay whatever, I think it's 72. You're going to end up paying that lower percent 72 times. It comes out to $41,846.52. Mr. Gallagher wins the lottery, gets $1 million. He has the choice of investing in a bank that pays 4.2% paid once a year or 4.2% compounded daily. How much more will he make if he goes with the compounding over 10 years? So when we look at this, I just pop the numbers in to the equation. Just remember, the formula that we've been using means compounding once a year. It's the same thing as if you put a 1 in for the number of times it's compounding. Now, the other one I did with compounding 365 times, so a very small part of the 4.2%, but you're going to be paid much more often. When you do your subtraction, you find out that you're going to get $12,966.65 more if they pay you daily rather than just paying you at the end of the year. And the reason why is because every time they pay you, you have more money in your account. And the next time they pay you, they're going to have to pay you interest on whatever's in your account at that time. So interest off of interest off of interest. The next one says, here is a graph. I showed you on the graph what f of x looks like. It starts at 100. It doubles for each value of x. And then it says, suppose you have g of x, which is 50 times 1.5 to the x. Will the graph of g meet the graph of f for any positive values? The answer is no, because the initial amount is lower and it's increasing at a slower rate. So how could it ever meet? I went over and plotted the points just to make sure. And and I got no, lower original, and the graph increases slower, so it will never meet. The next one, you are supposed to be coming up with your exponential function here. You want to find out between 0 and 1 what percent is remaining. So in this case, you can see that 80% is remaining. It decayed by 20%. So I had that 0.8 as my decay factor. I need to know my original In this one, I was lucky because they show me what it is. I don't have to solve for it like we've done in previous lessons. You can see it's 80, so you put the 80 in there, and you get y equals 80 times 0.8 to the x. All right, hopefully that all made sense. Thanks for watching.